Hello. This presentation will unpack problem 1 within the mini project. This problem is about a spool of sheet metal which rolls along a truck. We look at different parameters which affect this in order to evaluate the angular acceleration of the spool. To set up this task, we developed a free body diagram to demonstrate and visualize the forces acting on the spool. The diagram identifies the normal weight and frictional force. We also created a kinetic diagram to outline the angular and translational acceleration. Through analysing these, we were able to determine the known parameters, which played an integral role in solving the problem. Shown here are the equations, theories, and principles that we used to solve and understand the problem. Following this, we looked into the specific calculations. These are shown below. We applied Newton's second law and rotational dynamics, carefully substituted equations, and used algebraic manipulation to solve for angular acceleration. I will walk you through the theoretical framework and equations we used to analyse the motion of a rolling spool. Beginning by calculating the moment of inertia of the spool using the formula mass times radius of gyration squared, with a mass of 500 kilograms and radius of gyration of 0.5 meters, we received the moment of inertia equals 125 kilogram meters squared. Next, we applied Newton's second law in the horizontal direction, where the only horizontal force is friction, thus determining that force of friction equals mass times linear acceleration. We also applied the rotational motion about the spool's center, where moment of inertia times angular acceleration gives a relation between linear and angular acceleration. We then used the rolling condition, which tells us that the truck's acceleration equals the spool linear acceleration plus radius times angular acceleration. Solving for the spool's linear acceleration and substituting it into our moment equation gave us our final formula, where angular acceleration equals radius times mass times truck acceleration divided by the moment of inertia plus radius squared times mass. Plugging in the numbers, we determined that the angular acceleration was 3 radians per second squared. Shown here are two graphs which plot frictional force against the acceleration of the truck. The pink line is used to show the maximum amount of static friction, and the point of intersection represents where the acceleration takes over the static friction, which results in the rolling of the sheet metal. Task 2 analyses a similar scenario without knowing if slipping occurs. We are given a range of parameters, which we then used manual calculations to solve the problem at the upper boundary of the static friction. We then used MATLAB to simulate the same scenario. As shown, we received the same outcome using both techniques. We then used MATLAB to simulate various scenarios by changing the static friction between the minimum and maximum range. In doing so, we determined that this indicated whether the spool was going to slip or not. Thank you for taking the time to watch this presentation.